Hi guys. So we continue with our 10.2. I'm gonna do the same material as we cover the same material from the book, but I'm gonna divvy it up a little bit differently because some sections are very long and I rather split them in two, and sometimes I might combine a section 10.2 and 10.3 or something. You'll see. So today I'm gonna concentrate on bipartite graphs and a problem that is called matching, the matching problem. But before I do that, I want to give one more discussion about degrees and another definition that we need. I want to address the following problem, right? So just a couple of more things that we can do. Suppose I want to make a graph. So this is now a problem of can I make graphs? And that's not an easy problem to solve. So here is an example of a graph that I want to make. So I want to make a graph with 5 vertices, and I'm going to assign degrees. I want this to be degree 3, this is degree 3, this is degree 3, and this is degree 2, and this is degree 2. And this is degree 4. Sorry, that's what I meant. So, can I make a graph like that? You would say, oh, you have to try a little bit, but I'm sure you can. Well, no. And so we have one main theorem that tells us when you can or cannot make a graph. Remember, we had this theorem 2, it was called. Theorem 2 said that the number of vertices, I'm sorry, sometimes use the wrong word here. I don't know why I do that all the time. The number of vertices of odd degree. So that number, that we cannot say what that number is, we can only say one thing about it, is even. Now look, how many odd degrees do I want? I want 1, 2, 3 odd degrees. No, that's not possible because it has to be an even number. So there is no graph that fits the pattern. Now, it doesn't mean that if you fit the pattern, you can be drawn. Here is an example of something that fits the pattern. So this is basically the only thing at the moment that we have to dismiss the existence of graphs of this type. Okay, so but here's another one. So suppose, let me first draw. This time I'm gonna have 6 vertices, and I want the degrees to be 5, 4, and 2. So now notice that the odd vertices are the number of them is 2, which is something that it should be. Otherwise, we are in trouble, right? We cannot make a graph if that's at least not verified. But just because it's verified doesn't mean that there's a graph. And let me show you why there can be no graph here. So suppose we have to try. So we try to make a graph. Now, in general, of course, there are many possibilities, right? I mean, if I have to, like, for instance, in the previous case, I know it's not possible, but before I realized it was not possible, I might have tried a little bit. Sorry, I should not try to not get this. So I could say, okay, I'm going to connect this to that, and this to that, and then has another one, so I do that. And then I'm going to do this to that, and I'm going to do this to that, and I'm going to do this to that. Oh, no, because then if I do this, then this has degree 3. No, so, okay, no, I cannot do that, so back up. So a lot of times you have to back up and try and figure it out. Now, try as much as you want. It's never going to work because of the theorem, right? So, okay, just scrap it out here. But now what about this one here? Okay. So what is sometimes useful then to do is to look at vertices with extreme degrees, either very big degrees or very small degrees. If the degree is 0, then you know, okay, I don't have to put any edges to that thing. So that makes it very simple. If the degree is 1, a so-called pendant, so let me write that word, the degree 1 vertex is also called a pendant in the textbook. I'm not going to use that word too much, but just you might hear me say it once in a while, because it's kind of, if it looks something like this, right? If you have a graph like that and you have a lot of connections here, but this guy is kind of barely hanging on, pending. I don't know, how do you want to think of it? Okay, try to make a graph now. I'm going to look at the ones of degree 5. Now, there are only 6 vertices, so apart from itself, the top one, I have no choice. If there have to be 5 neighbors, can only be everybody else. So if this, so just the fact that this is degree 5 forces me to have these 5 edges in there, right? There's no way around it. There's no other thing. These are all simple graphs, right? I cannot draw multiple edges. So what the same for the bottom guy, the bottom 5 guys. So I have to go to everybody. Okay, so that's good. So now this one, let's now color the ones that we are, let's put them green, the ones that satisfy what we want to do. So this is now degree 5, so I shouldn't add anything, which is impossible. I shouldn't add anything. This is degree T, so 2, I should not add anything anymore. Okay, good. Now what about the middle ones? Oh no, that we need edges there. We need to draw an edge to, I can draw this edge, but I need still one more. But remember, the green ones are already taken. I cannot draw edges to them anymore because they have already the right degree. So there's nothing left here. So what I'm missing is, so let me put it in red here, where is this going to go? And where is this going to go? There are no points anymore. And so although this graph satisfies the theorem, there exists no graph of that shape. And so there will be some homework problems where you have an assigned number of degrees, and then you have to try to find one that has this degree, or show that it doesn't have a degree, or argue that it doesn't have a degree. And it's, as I said, not always easy if you don't have if the theorem is in this is a more special case, the theorem is satisfied. Often we're going to use the theorem here, so don't forget that for that homework problems. But if the theorem holds and there is a graph, that's a different issue now. Now you have to construct a graph, which is also something that might take a little while to try and error. But there are never really big graphs. It's not, if this would be what 15 vertices and so, or 100 vertices, then it would be difficult, but not with a few numbers. Okay, so the next thing I need to talk about is the neighborhoods, because this is going to be important also for what we're going to discuss next. The neighborhood of a vertex A, that we denoted N of A, that is all vertices adjacent to A. I think I already discussed this last time, but we're going to work on these neighborhoods. And more generally, the neighborhood of vertex A, so that's for A, the neighborhood of a subset of vertices. So now we have a subset. I'm going to write my subset as sigma, because I want to use a different letter for a subset here. And so the neighborhood of sigma is the neighborhood of all the vertices in sigma. So you sum over all the vertices in sigma. In other words, another way of saying that is all the vertices adjacent to some vertex, not to all vertex, to some vertex of sigma. Okay, so let's take a simple example here. Let's use this graph that we have here. You say, oh, it doesn't exist. Well, I'm going to make it exist, right? So we were missing one thing here, so I'm going to put one extra dot point in here, and it will all be solved, right? So now we have 4, 4, and this is now also 2. Okay, so now we have a graph that works, and I think I hope I was supposed to draw this. Oh, there's a couple of things have fallen. Sorry, these were there, right? But they accidentally got erased. Okay, so now we have a nice, good graph. Well, so let's calculate the neighborhood of the following set. I'm going to make it orange. Let's take it this guy. Let's use orange here. So this, and this. So what is the neighborhood of the orange? How do we find that? Well, we look at all things that are neighbors adjacent to one of those. Now, be careful. So in order to do that, the best way is to just look at the neighborhoods of all the guys. So, okay, I think I have to give them names, because otherwise I'm going to get in trouble, right? Okay, so that's the one thing. Sometimes we have a graph without names, but in order to talk about the graph, we have to give names to the vertices. So I'm going to name the vertices. I'll do that in red, because the black is the degrees, right? So then red is going to be the names of, so I call it just A, B, C, D, E, F, and G. Now, what names you take does not matter, right? So the orange set is A, E, F, and G. So in order to calculate the neighborhood of orange, I have to calculate the neighborhood of A. What are the neighbors of A? Well, the neighbors of A are, I'm going to need some space, but that's okay. I'm going to erase my definition. Okay? You've seen the definition now, so let's get myself some space. The neighborhood of A. So that is B, C, D, E, and G. Not F, because remember F was something that I added later. The neighbors of E. I don't need the neighbors of B. I need the neighbors of E. I'm calculating the neighbor set of each of these guys, and then I'm going to put them all together. So the neighbor set of E. So what is connected to E? That is A. A, D, E. Sorry, I messed up my. I'm sorry about this. I think I messed up my graph here. It's no longer the graph that I intended to do. Let me make the graph again. Something got erased and I put it in wrong. I don't know whether you noticed this or not. So we had. This is what the situation was, right? So we had this, and then this guy here. So this has to be 5, 5, 4, 4, 2, and 2. And we had this, and this. And we had that, this. And then we had these two guys connected, and then this to that. Okay, so now, and this therefore has also degree 2 now. And then we gave names to them. So this was, I'll do it in different color now. A, B, C, D, E, F, and G. I think the names are now a bit different, but okay, that's no big deal. And the orange set, that was this guy, this guy, this guy, and this guy, I think. It doesn't matter. I'm choosing now those 4, okay? So now I want to calculate the neighbor set of the orange, or the orange set here. So the orange set, I mean the ones that are all orange, right? And so in other words, that is the neighbor set of the set. Let's write down the set A, E, F, and G. So I want to calculate this. So what is this, we ask? Well, we have to calculate each separately. So what's the neighbors of A? The neighbors of A are B, C, D, E, and F. What are the neighbors of E? I'm only concerned with those ones, so I only calculate those. A is a neighbor of E, D is a neighbor of E is a neighbor of E, and G. There has to be 4, right? Because it has to be degree 4, okay? The neighbors of F, that should only be 2, that is D and A. So let me put them in order, perhaps. Again, it's not necessary. Remember, sets are not ordered sets, but it's easier to see if I put everything alphabetically. And of G, that's B and E. Did I hope 5, 4, 2, and 2, at least the degrees are correct. So what is now this set? So the neighbors of the orange set. Oh, this means all the orange ones, right? That is the combination of all of them. So let's see. A is in there. Okay, so I have A already. Oh, then B. Sorry, I just scratched that. But we have B. C is in there. Okay. Then the D is actually there quite a lot. E's. Okay, we have an E. F. Yep. And G. Yep. Notice that therefore the neighbor set of these 4 is the whole set. Okay, but that's of course not necessarily the case. So let's do one more. What is the neighbor set? Let's take a little bit different set. C, F, and G. Let's call these the red points. So I'm going to make them, or let's take a color that is different than purple. No, that's too close. No, purple. Okay, C, F, and G. Okay, so what are the neighbors? These are purple neighbors. The neighbors of C. Well, that is A and D. We had that already, right? No, we hadn't calculated. The neighbors of G, that is B and E. And what are the neighbors of F? The neighbors of F are A and D. Yeah. So what is this neighbor set now? Well, we put it all together. We have A, so we have taken care of that. We also have B, so we scrap that out. There's no C. The next one I have is D, so this goes also, and then an E. Okay. So notice that things can happen here. In this set, the neighbors of this set, none of the neighbors belong actually to the set. Whereas here, many of the neighbors are also part of the set. So you can have a little bit of everything can go on. So the neighbor set is depending on the subset of vertices you can have different types of neighbor sets with many more or many few elements. So the number of elements is also, it's not clear at all. We cannot predict that. Okay, and that's important as we're going to talk. Now, so we get to our main topic, and that is the bipartite graphs. So a bipartite graph. And let me analyze the word bipartite first. Well, it has two parts. In bi, which we know means two, right? Bicycle, two wheels, and you can come bipartisan, right? Something that we kind of don't see much nowadays anymore. And then part, well, part. So this is a graph that has two parts, and the two parts are two parts of vertices. That's what it refers to. Okay, so there are, if you want, top vertices, bottom vertices, or V1 and V2 they're sometimes called, or sometimes they're called left and right. It depends a little bit on how you arrange the vertices. There's no common agreement on how to call these two parts, but the fact is the two parts. What do I mean with that? So let me visually say there is like we have these vertices on one side and we have these vertices on the other side, and so there's kind of a divider somehow between them. That's not really part of the graph, right? But just visually, I'm writing this line so that you see visually that they are different. And what is the deal is that if you're on the left hand side, you can be connected to a guy on the right hand side, to several guys on the right hand side. Let's say this one. So this one is not connected to anything, fine. This one is connected to all three, say. Oh, sorry, to all three. And then this guy is only connected to that. And that's it. In other words, there are no connections between guys on the left, between themselves, and no connections between guys on the right, between themselves. Okay? And later on, one very visual or like in way of representing this is we think of this, and we'll call it actually that, the marriage. Like these are boys and these are girls. Okay, and okay, you know, mainstream textbooks and so kind of always are traditional in the sense they think heterosexual, right? They don't consider gay to be, they don't take that into account. That's not fair, I agree. But okay, this is now all. Remember, this was from the old days that people came up with it when these things were like, no, you don't talk about these things. So, okay, so men would marry women, right? So yeah, these were done the men, and they were trying to match them with girls. With women, and so this is the matching that we will talk about. Okay, so but first of all, a bipartite graph is a graph. So formally, the vertices are divided in two disjoint sets. So these are disjoint. In other words, they have nothing in common, and no vertices in V1 are connected by an edge. And the same is true for V2. In other words, the only edges we have are across. Okay, so sometimes we denote it this way. Sometimes we write it. Another representation is to do it this way. And so we kind of take two Venn diagrams almost. And so this would be V1 and this would be V2. And then the whole thing is that between the guys in V1, there should be no edges. The edges can here, in this case, only go down. So we have, for instance, this and that, and we have that and this, and we might have this, and then this, and this, and this. But the number, again, we have now all all possibilities that are allowed as long as it's a simple graph. Notice that these are still simple graphs, right? It's not that they look different because I have separated the edges from each other. The vertices from each other. I made them left, right, or bottom, top, bottom. But in principle, these are just graphs. And so that's the first problem that we can ask now is, well, okay, if these are graphs, are they bipartite? If I just give you a graph, is it bipartite? So let's start with a simple example. Let's take C6. What is that? You should remember C6 is the graph, the cycle with 6 points. Okay, so it's basically the hexagon, if you want, right? So we have the edges are really the edges of the hexagon. So this is my this is my C6. But I'm claiming it's a bipartite graph. Now, naively, you'd say, okay, yeah, so sure, okay, I'm going to take these three. So let's do it in a different color here. Let's do it red. I take these three, and that's my V1 and V2. No, because this is not allowed. If this is your V1, the top is V1, then there should be no error here. No edge here. So no, that's a wrong choice. Oh, okay, that's not the wrong choice. So perhaps divide it this way. That's going to be the same problem, right? So now the more you try to do this, you say, this doesn't work, Professor, you're wrong. This is not a bipartite graph. It is. Look, I'm going to color the ones. Let's look at this guy. Now, if I want something to be, if it want a bipartite, what cannot be in my, let's call the purple guys. The purple guys are the ones that are going to be the top guys, and I call them different color, green or something, will be the ones in the bottom. So I'm trying to construct, I'm just trying to rearrange this graph so that we would have guys in the top, that would be the purple here. So here we would have a purple set, and then we would also have a green set here of vertices, and then it should be the same graph, right? I'm not making a new graph, such that the only arrows are going across. Nothing there, nothing there. Okay, so I'm deciding to make this guy a purple guy, but that immediately tells me that his neighbors cannot be purple, because purple should not be connected. So these have to be green, and they have to be green. Now, reason with green. Green can, the neighbors of green are this guy, which is a purple guy. Okay, this is going to be here. The greens are going to be here. Where is this guy going to be? It cannot be a green guy, because then there would be an edge between the two greens. So it has to be a purple guy. Right? You see? This has to be purple. But then this, for the same reason, this has to be purple. And what can this be? Well, it can only be one thing, right? It has to be green. So if let's now give names to, let's do it in red. The names of these things, let's call the A, B, C, D, E, and F. Suppose that these are my vertices. Then the purple ones will be A, C, and E. Notice that what we did was we skipped one each time, right? And what would be then the green ones be? B, F, and D. And how does it work? Well, A is connected to B, and A is connected to F, and C is connected to D, and C is connected to B. Okay, and then E is connected to D, and E is connected to F. We get a very nice symmetric pattern, like a little papillon, or I don't know what you call it. Something like that. So, and this is the same graph, just the order in which I put things graphically is different. Graphically, I have separated them in a different way than this way. So these two graphs are the same because they have the same vertices and the same edges, and we will, next lectures and so we will talk about we call this isomorphic graphs. But they're actually really the same here. So, in other words, a simple graph is a bipartite graph. At least some simple graphs are part of a graph. So are they all? Well, let's look at the next one. Let's look at C5, the pentagon, which I very bad at drawing. So here's the pentagon. Okay. So let's already give it names: A, B, C, D, and E. Okay, I'm going to do the same. Now I'm going to choose again, put one on top, one on the bottom. Doesn't matter what is top, what is bottom, right? So I'm going to say this is going to be a top guy. Okay. Now I know that because that's top guy, its neighbors should be bottom guys. So I'm going to make these green and this green. But now I know that because B is green, it cannot be connected to another green, so this has to be a top guy again. And same for E, and it has to be top guy. Whoa, 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 what happened? What happened here? This thing happened. Now I have two purple guys connected to each other. No, that's not possible. So this is an example of a graph that is not bipartite, where this is bipartite. So this is a bipartite graph. So this is bipartite, and this is not. So bipartite graphs, sometimes it's very clear that they're bipartite. If you see it this way, it's immediately clear. But sometimes if they're given in as a regular graph, it's hard to tell whether they are or not. How do you know this? Well, actually, I already gave the answer. This is so-called the color theorem. And I'm going to say it in words because it's really what you've done. If you can color the graph, the vertices in two colors, such that no two vertices of the same color are adjacent, then you have accomplished a bipartite graph. And in fact, the colors then form the two parts. Let's do this on an example here. I'll do a little bit more complicated example. Okay, this is really a complicated example. I don't know when I want to draw all this. Okay, I'm going to try to do a little bit of this. It's going to take me a little while to draw, so bear with me. So I'm probably going to draw it wrong. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. No, okay, so one more here. Okay. I should have, if I had the time, well, okay. I'm going to label them, and I'm going to label them, yeah, I don't know what to say here. Wait, okay, give me a little time here. So I'm going to call this O, I call this W. Okay, so here we go. So this is going to be A, this is going to be O. I'm going to call this F, and this L, and this K, and this is E, and G, and H, and I, and J, and W. I think that's all I want. Okay. And now, okay, we have an arrow from A to J. We have an arrow from A to H. We have an arrow from A to K. You have an arrow from F. Okay, that is A. Let's go from O goes to H, and then F goes to L, and then F also goes to C. F goes to C. Where is C? Oh, I have no C. Okay, sorry, I forgot C. So C comes in the picture. So this is F goes to C, F goes to K. Okay, and then H goes to A, it goes to O, it goes to E, it goes to W. I'm sorry, I'm drawing this graph here and I'm copying it, but copying graphs is not easy because, yeah, it's lines and lines that are connected, so you have to be very careful that you don't forget anything. Okay, so I have O, I have A, I have E, and I have W. I think I took care of, okay, let's take care of G. G goes to C. Where is C? Oh, C was there. Okay, yep. That's it. I goes to C. Where is I? I goes to C. Okay. And I also goes to F. Okay. C, I, J. What else do I do? W. W goes to J. And W goes to H, right? That's okay. I have this already. K. K goes to F. to L. I don't have that yet. No, K doesn't go to L. K goes to F, K goes to A, I have that, and K goes to E. Okay, I don't have that yet. Yeah, I'm sorry, I'm not very systematic, and I'm worried that I'm going to forget something. Okay, so let me write down the degrees here. Okay, so let's write down the degrees. I'm going to do the degrees in red. So that's degree 3 here. Then O has degree 1. F is supposed to have degree 3, and I have 4 here. Okay, so that's where F is wrong. F should be connecting to I. Yeah. F should connect to L, right? And F should connect to K, right? So F should not connect to C. Okay, sorry. So this one was wrong. Okay, so now this is 3. I'm sorry. I apologize. I have to do this a little bit. 1. K has degree 3, so okay, I'm good here. W has degree 2, I'm good. J has to have degree 3. Oh, something is missing here. So A goes to J. I don't have. Oh, yeah, A to J I have. J to W I have 2. Whatever. J to C I don't have yet. So J goes to C. Okay, so now J has degree 3. That is also correct. That is how I can verify that I have drawn the same picture. I has to have degree 2. Yeah, that is correct. H in my picture has 1, 2, 3, 4. Oh, this J should not. Okay, this J is very badly drawn. The last one I drew was very badly drawn, so I'm gonna. It's not gonna go to H, right? It's not going to H. So this is. Oh no, I want to do this in black. So this. Okay. Remember, crossings, if they're not bold, like a real vertex, then they don't mean anything, right? Okay, so I has now degree, H has now degree 1, 2, 3, 4, that is correct. What else? G has degree 1, that is correct too. E, supposed to have 2, that's correct. And C has degree 3. Okay, so I copied my picture that I had, and this is how it looks like. Okay, so I drew a bunch of nodes on the top and a bunch of vertices on the bottom, but that's not the right division to make it bipartite, right? Is this bipartite? That's now the question. Is this a bipartite graph or not? As such, it doesn't look bipartite at all, because, as I said, the top ones are connected with each other. There are connections downwards, but definitely the way it's arranged, it's not bipartite. It doesn't look bipartite. So let's do the coloring. So I'm gonna start coloring. Now you might say, how do we know where to start? Well, that's the beauty of it, right? It doesn't really matter. Start with whatever color you want, with whatever node you want. If you would have, you say, I'm gonna make A green. But if you would have instead chosen to make A purple, then the colors just are switched. Green becomes purple and purple becomes green. So it doesn't. The first choice is done, but once I make that choice, you see everything else is kind of set. And let's see. Well, A has 3 neighbors, so all these 3 neighbors, and I have the degree here. By the way, how many edges are there? Just for the fun of it, the number of edges of my graph is. Okay, I'm not going to count this. I'm going to do this. 3 plus 3 plus 1 plus 3 plus 1 plus 3 plus 2 plus 1 plus 4 plus 2 plus 3 plus 2. All this number divided by 2. Why? And remember, that's one of the main theorems, right? If you take the sum of all the degrees, that's twice the number of edges. So we have here 6, 7, 10, 11, 14, 16, 17, 21, 23, 26, 28. So this should have 28 divided by 2, should be 14 edges. Now you can count the edges, but try it. It's not so easy to count edges because, okay, how do you make sure that you double count an edge, right? You can scrap out the edge or something like that, but it's on a picture, graphs are very beautiful things and very nicely pixel representations, but once you to start working with them, you realize that the drawback of pictures is that, yeah, there's inaccuracies. It's hard to see sometimes what goes on. So I challenge you to count the number of vertices, edges, and see that it's 14. Now, I'm not saying it's hard, but it's you have to keep your your mind clear. You have to be systematic to do that. But okay, coming back to my coloring. So I have A has 3 neighbors, and all these 3 neighbors have to be purple, because in a bipartite graph, greens cannot be connected to greens. So these are all purple. Okay, that takes care of A. So we can now go through this thing. We should again be systematically. So let's go alphabetically. Okay. Oh no, sorry. Sorry, I shouldn't say that. If you want to go alphabetically, the next one you would look at is C. But C has no color yet. And once I have started coloring, I cannot just guess what the color of this thing would be. Because I said, by making one guy color, everything else gets the right colors if it's bipartite. If it's not bipartite, you get this clash where 2 neighbors have the same color. But if it's bipartite, once I decided this is my green, everything else has to come out. Well, it's not entirely true. There's a so-called connected graphs. This is true for connected graphs, but let me not talk about this now. This is something we'll talk about later. Okay, so I should now go alphabetically to the next one that is already colored. That is H. Okay, so H has 4 neighbors. All these 4 neighbors have to be green. A, we know already is green, but that also E, O, and W. Okay, let's alphabetically go to. So okay, let's mark also which one we have done, perhaps. I've taken care this. So this one is taken care of. This one is taken care of. So I've validated the color, so to speak. Okay, I'm going to the next available. E seems to be alphabetically the next one. I'm not saying that you have to do that. I'm just saying you have to be systematic. And for me, to make sure that I don't forget anything, is I'm going just alphabetically, right? So I'm going to E. E has 2 neighbors, and both of them should be purple. And that actually is already true. Both are colored. So this is also a validated vertex again. So I should go now to the next available one that is colored, and in alphabetically that seems to be J. Okay, let's look at J. J has 3 neighbors, and they all should be green. Okay, 2 of them are already green, but the third one is not colored yet. So that would be this guy, right? Right? Yeah. See, it's good to have the degrees, then I know what I look for. If you don't have the degrees, you might don't. I mean, you see, okay, you have to follow this edge, so to speak, right? So it takes a little while to see what goes on, especially because there are many edges going on. Okay, so C has been taken care of, so that's also validated. What is alphabetically the next one that I have not yet colored, one that I have not yet talked about? J. Oh no, I did J. Oh, sorry. Oh, okay. No, I misspoke, right? Yes, sorry. I took care of J. I haven't validated C yet, so let's do C now. C has 3 neighbors, and they should be all purple. J is a purple neighbor. What's the other neighbor? Oh, I have not colored I, so they were purple now, right? So this becomes a purple one, and this becomes a purple one. Okay. And now I've validated C. Okay, there's no conflict here with C. Next one, alphabetically colored one, alphabetically, is G, I think, yeah? So G, but that's fine, it has only 1 neighbor, so let's go to the next one, H, no, I is the next one, okay, I has 2 neighbors, one of them has no color yet, so I'm going to do that now, that is F, right? So F, okay, so I is now correct. Next, alphabetically, now F comes there. I should look at F now. So for F, I have 3 neighbors. They all should be purple. Let's see. L, K, and I. Yes, that's good. So I colored one more. So F is now okay. So very good. F is no problem. Alphabetically, what is still left? As far as I can tell, L, I guess. At this point, it's not so necessary anymore to alphabetically. I mean, in fact, since I circled what I have done, I don't need to do alphabetically. I just need to pick one. But just for you and for us to talk about it, I always take the alphabetically one that I can available. But okay. So notice, by the way, everything has been colored yet. So at this point, I have a proposed division, but I have to check that it is correct. So I have to check everybody else. Is this correct? Yes, there's no purple connecting to this one. K, I haven't checked K. K connects to green only. Is that the case? Where is it? Yes, all three are green. Okay, so K is okay too. Let's look at O. O is correct. And then W finally. W is connected to two purple. Yes, so everything checks out. I've now circled all of them, so all have been verified. So I have shown that it's bipartite. And so what is the bipartite, guys? The purple ones and the green ones. Okay? Now, okay. That's how you check that the graph is bipartite or not, and then you can rearrange it, redraw it. But I challenge you. It took me a while. Took me some time to do the drawing. So if you try it yourself, just drawing it with the purple on top and the green on the bottom, make sure that you don't forget anything. It's a challenge to make sure to copy. It's silly, but it's a challenge to just copy a graph, even just copying it. Other than taking a picture, I mean, just by hand copying it, right? Okay, so now where we can use this is, now let's talk about matching. And let me give an example first, what I mean with the example. First of all, I'm going to give you a bipartite graph here. And make it this one, and then here, 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 and here. And so there are gonna be people here. This is Alice and Bob. You remember, they are always there, Alice and Bob. And then we have Chia here. And then finally, let's call this Dimitri. Dimitri is here. Okay, so these four guys, and they form a team in a challenge, a quiz challenge. There's a team that they do these quizzes, and they have been each specializes in certain topics, and the topics. So the next round, they have been announced. The topics will be film, history, literature, and sports. Okay. Now, each of these have specialties, as I said. Like, for instance, Alice knows a lot about films and a lot about sports. Okay, that's are the two topics that she has been studying or she knows quite a lot about. Bob is very good in history, in literature, but he is also a sports fanatic, so he knows a lot about sports. Okay, Chia, she knows a lot about film, about history, and about literature. Okay? And then Dimitri, he's a film buff. Okay. So that's how it stands. Now, in this quiz, let's pretend, I don't know, probably there is such a competition like that. So for each topic, the team has to put one of their candidates in front and say he's going to answer the questions on this particular topic. Okay, so here we are. So we know these are the knowledges that Alice, Bob, and Chia and Dimitri have, and these are the topics that we have to now assign them to. So how is this team going to decide who is going to take which segment of the competition, of the questions? Okay, who's going to do the film questions? Who's going to do the history questions? Who's the literature questions? Who's the sports questions? That is what is called a matching. We're going to try to match each person with one of these accomplishments. In other words, these are the V1 vertices and these are the V2 vertices. You see that this is a bipartite graph, right? Because obviously we're not talking about the knowledge between Alice and Bob, and also film doesn't know anything about history. Knowing is a very restricted how to say, aptitude, so it only apply. You're gonna get this kind of bipartite graph out of it. Okay, so what we want is a matching. And we want not just that. Of course, we could match Alice with film, and that's it. So this is what we call a matching. So I'm going to do my matchings in, do it orange. So just this one edge would be a matching, because we matched Alice with film. So a matching is a subset of the edges but such that no vertex is an endpoint of. Let me put it differently. All the edges in this subset are different vertices. Subset of edges with different vertices. I think this is clearest if I say it is all with different vertices. So for instance, what I cannot do is match Chia with film as well, because Alice and film are not matched. As far as the matching is concerned, they don't exist anymore. So we could throw them out, and then we say, okay, I'm now going to match Bob with history. Okay, good. Okay, and so now, Chia, why don't you take literature? That's okay. Yep, okay. And again, we are satisfying the matching problem. But oh my dear, what is Dimitri going to do? We have problems. Dimitri doesn't know about sports. We don't want to put him towards sports. In fact, he hates sports, so he's not going to, oh no. So just try and error, like just trying like that is not always going to work. So the question is it actually possible? But yes, it is. But actually, in some sense, the clue lies with Dimitri, right? That's this is going to be difficult. So I'm going to try to do this I'm not going to be able to do this right without. It worked. I don't want to erase the. Yep. See, if I touch this, then everything that I touch is gone. Okay, so but it worked. The clue lies with Dimitri. Look, if we want to match everybody, and that, what does that mean? Matching everyone. Now, I should be a little bit more careful what I mean with that, but I'm going to say it later. That is called a complete matching or a perfect matching. And that's what we want, right? We want to match everyone. It's a complete matching. So if we match everyone, in other words, if everyone V1, so the correct way is a matching, a complete matching from V1 to V2. Everyone in V1 is matched to somebody in V2. Okay, that's called a complete matching. If we want to do that, look, Dimitri for this particular topics, he has only one topic that he knows is film. So we have to make Dimitri answer the film questions. Okay, so now what can we do here? Well, film is taken care of, so we could delete film and Dimitri. And okay, I'll do it. So it is not what you want to do on a test, because you cannot delete things and then not see them anymore, but on the video I can do this, right? So when I try to match Dimitri with film, I have decided this is the match, and therefore neither Dimitri nor film can play a role anymore, so we're going to delete the vertices. I'm not going to say much about deleting the vertices. It's discussed at the end of this 10.2. But what you need to do is, once you delete the vertex, you have to delete all the edges that come from that vertex. Okay, otherwise this edge is going to nowhere. So this means, what should I delete here? So I'm going to delete Dimitri. Okay, I'm going to delete film topic and everything that connects to film, which is also this guy. Okay, so Dimitri and. Okay, let me keep the connection here that we can follow here. So these two are matched. Okay, so now we see already that Alice has only one specialty left anymore, sports. So if we want to keep matching everybody, we should give Alice sports, otherwise she's not good for anything else. So Alice is going to be matched with sports. So that means that once I decided on this matching, Alice is no longer in play, so I have to delete Alice, okay, and I'll delete the sports. But that means if I delete sports here, if I delete this guy, okay, that worked perfect. Sports, okay. So we have matched Ali, just short Ali, okay. I know my SCA got lost. And now, look, I actually have now top possibilities. I can map Bob to literature or Chia to literature, because they're both expert in either. So therefore, first of all, this shows there is not just one complete matching, But there could be several ones, and here is one. The simplest one would be this and that. And now Bob is with history, and Chia is literature, and everybody is doing something. Great, right? So that's how you find a complete matching. Now, sometimes complete matches don't exist, and then we want to try to go as best as possible. This is what we call maximal matching. And the maximal matching is where we do not complete, because that would, if we can do complete, that would be maximal. But if we cannot do complete, for instance, I'll do this. I'll do it right here. Give me an example now of why it's not. Let's do same guys. So here is Alice again. Alice, Bob, Chia, and Dimitri. And now the topics are film again, but spelling, languages, foreign languages, oh dear, and cars. Now, how does it go? Alice is from before. We know that Alice was knew about film. Yeah, sorry. Now some of the things has gone, but trust me, Alice was good in film. Bob seems to be good at spelling. Bob is also very good in languages, and of course, being a boy, he likes cars. Okay, so that's that. Then Chia is knows a lot about films. She also knows about literature from before, but and from history, but unfortunately these topics are not there. So the only topic that she knows is actually film here. And then Dimitri also knows a lot about cars. He also knows film from before. We know that he knows film, and that was one of the specialties. And then spelling. He's also good in spelling. Okay, we go. Is there a complete matching? So let's find the complete matching here. Now we see we are facing a different problem now. Before, when we try to complete match, we know that if they have only one specialty, these guys, we have to give them that specialty. But look, both Alice and Chia are competing for the same specialty, film. They only have one specialty, Alice. So let's make a little bit now. Let's make the neighborhoods list, or what we call we will call later the adjacency list, but I'm going to call now the neighborhood. So here I'm going to be the neighborhood of the vertex, and here we're going to put the vertex. So let's do this. So we have Alice, Bob, Chia, and Dimitri. Now the nice thing about bipartite graphs is you only have to list the neighborhood to know the whole graph. It's enough to know where the top guys are matched with, because that's the only matching can exist is with top guys with bottom guys. And so if I give everything that the top guys are matched with, I know everything about the graph. So Alice is film, Bob is spelling, I'm going to abbreviate, spelling, language, and cars. Chia is film, and Dimitri is film, spelling, and cars. Okay, so now we see it here. We see it more clearly. A and C both have degree 1, so perhaps it's good to write the degrees also. It doesn't need to be, but it helps always to know a little bit what's going on here, because we want to take care of the ones with the lowest degree first, because they have the least amount of choices. And Alice has only one choice, so we should, if we match, we have to match Alice with film. But the problem is that also Chia only knows film, so we have nothing left for Chia anymore to match. In other words, if I do this erasing thing, once I make a match, remember I said we want to get rid of the nodes, so we have to get rid of this node and of this node, and then we have the matching here for Alice and film, so that matching is still there. Chia has nothing to do anymore, everything is lost now, and so we can only assign Bob and Dimitri to something, which let's redo it. We can Bob to spelling and Dimitri to cars. That's it. And then language, forget it. We forfeit on languages. This is a case because we have only not a complete matching, but and this would be therefore a maximal matching, because complete would be all 4. Maximal is at least one less. Now it could even be that that's not possible, and then we have to try 2 less and 3 less and so on. But in most cases, if you're gonna do a maximal will be just one guy is kind of left out. Okay, so now comes our main theorem. How can I figure out? Okay, here we tried it and we see it immediately didn't go. But what if in this more complicated guy here, let's go back to